Okay, so what we have here, this demo is called a wave table. And what it is I've got water here. Okay, this isn't like magic or anything. I poured some water onto this piece of glass. Okay, this is just a thin piece of glass, just a thin layer of water here. Okay, there's a mirror underneath. See mirror? And this is a plastic board here up on the front, held up by some Velcro. And so what happens is if I touch the water, you can see it on the screen. Can you see that?
Where's the water?
Right here.
Oh, it's on the board.
That's the water. Alright? Okay, you want to turn up the lights for me? Okay. So, to go along with that, we have a light source right here, shining down, help us see, and then we've got this guy right here, which is our function generator. Okay, we can use it to create ripples in this little tank of water. So I'm going to start with just a little rod here, and so it can make some nice circular ripples. So let's turn up the amplitude so you can see what it's making. So let's turn down the frequency. It's a little bit easier to see. Like 10 or something. So do y'all see these little kind of circular waves moving outward here? So do y'all see it's just moving this thing up and down, and it's making these circular waves go on out from it. Everybody okay with that? Okay. So as I increase the frequency, how fast this is moving up and down, you'll notice things change. Okay? So if I crank it up to like 20 here, it's still moving up and down, it's still creating these circular ripples, but it's a little bit harder to see. Would you all agree with that? So what I can do is, first of all, I'm going to move this back a little bit, because I really just want the edge here. So, move up there. It's hard to see, so what I'm going to do here is I'm going to flash this light, or strobe it if you will, at the same frequency that this thing is moving up and down. So as a result, you'll only see it when this light flashes. Okay, y'all ready? So, what do you see?
It's like it's standing still.
It looks like it's standing still. Now, is it?
No.
No. But it's only flashing every, in this case, 20 hertz, so 20 times per second. So it looks like these waves that I've created are just standing still. Now, they're not, but it's really useful because now we can see things a little bit better. Y'all see that? Mm-hmm. And so here we have the light areas and the dark areas. The light areas actually correspond to troughs, and the dark areas correspond to crests. So it's making what type of a wave? Transverse, right? Like you'd have on the surface of water. What type of wave is transverse? Sound or light?
Sound.
Light. Light is transverse, sound is longitudinal. So, we're still learning here. Okay, so I need a volunteer here. Alright, so come on up here. I want you to stand right there. And I want you to kind of lean out of the way so everybody can see. Put your fingers, put two fingers, like one on each of these light areas. Okay. You got it? So, you can put your fingers right up on it. It's not going to smudge or anything. So what I have her doing here is she's measuring from like a trough to a trough. So what is that distance? What do we call that?
Wavelength.
The wavelength. Okay. So remember, the frequency is dictated by the source. So in this case, this thing. So unless I change this, the frequency will stay the same. But the speed of the wave is caused by what? The medium. So in this case, the medium is what? The water. Okay. So the speed won't change. But if I change the frequency, the speed stays the same. So what has to change? Wavelength. Good. Okay, so here I go. I'm going to increase the frequency And so she's holding onto the wavelength there, okay? So don't move your fingers, all right? You ready? Calm down. Okay, so here. Did she move her fingers?
No.
Turn that up a little bit so y'all can see it better. Did the waves get smaller or bigger? Was the wavelengths the same size? Okay, so they got smaller, we all agree? So my frequency went from 20 to 40. So I increased my frequency, but what happened to the wavelength? It went down. They're inversely related. Do y'all see that? Because V equals F lambda, V being the wave speed, that didn't change. So since the frequency went up, the wavelength has to get smaller. Okay? So as I turn the wavelength down here, zoom it down. So here's like 30. Y'all see that? You see as I get less frequent, the waves get bigger? Y'all see that?
Yeah.
Alright, thank you. Okay, so that's the first demonstration, that the waves change size. Now what I want to show y'all is I can strobe this light to make it look like the waves are moving, okay? So if I offset the frequency of this light by, say, 1, I can make it seem like it's moving in one direction. What direction does it seem like it's moving? Yeah, it seems like it's moving this way. That's because the strobe is slightly ahead of the frequency generator. So here, if I go behind, that looks like it's moving to the right. Y'all see that? And so I can use that to see things when they're moving. So the first thing I'm going to do here is I'm going to add another little dot. And so this shows us some interference patterns. So here, do you see the interference pattern? This crazy looking stuff here in the middle. Yes, no?
Yes.
Yes, okay. So you see this interference pattern here, and I can, like this, so it's created over and over, and so the interference pattern spreads out, okay? So we talked about nodes and antinodes. So like these areas that that are very light where they cross over, those would be like your antinodes, where the waves come together, and then the dark areas would be kind of like your nodes. Or sorry, the dark area and the light area would both be antinodes, because they're both like crests and troughs. But this like slightly gray area here in between, that's where the water's actually flat. So do y'all see these like kind of like spokes that come out from it?
Yeah.
Those are just nodes. So just like no vibration is happening all along this spoke here. Alright, so that's enough of that. Let's do some plane waves. Alright. So here, I have this little bar. Okay. So here, they're both shaking up and down, but they're shaking this bar, so we get some nice, straight, fairly straight lines. Everybody see that? So we can use this to demonstrate some things. So let's start with diffraction. What is diffraction? It's the bending of a wave, bless you, when it passes through a barrier. So here I have, or bending around a barrier, I should say, not passing. So here, I'm blocking everything with these barriers here. Let's increase our frequency here. There's looks better. So here this is blocking, so the waves are coming out, they're hitting the barrier, and they're mostly bouncing back. So you get this pattern here in between the two. Y'all see that? Oh, come on, we're filming here. Okay. But do y'all see that some of the wave passes through this little gap? Y'all see that?
Yeah. Yes.
But does it just go straight out? No. It kind of bends around the barrier. So you'll see that it's diffracting there. So that is diffraction. Everybody see that? So remember that happens with all waves. Okay? So here I can use another small barrier and put it in between these two and get two holes, two gaps. And so I'll get diffraction from each one. And so each one's diffracting, but they'll... Oh, no. Move that a little bit closer. So it'll get diffraction from each one, but we get this nice interference pattern where they're coming together. So what does this look like? Does this remind you of anything that you just saw? Speak. What did I just show you before this? Well, they're still transverse waves. But I showed you the waves being made by these little dots. Remember they just made like little circular waves? You'll see this looks just like that? And so it looks like, you know, I'm just using a little circle here for each one, and they're adding up to this interference pattern. It's kind of weak. That's a little bit better. And so that's diffraction with interference. All right, so any questions thus far? A few more demos here on the wave tube. No questions? All right. So now we have this curved barrier. So when I put this straight barrier in, you see that the wave comes in, hits the barrier and bounces off. And so, what is the law of reflection? You already forgot.
That the ray that hits it is the same degree off of it.
Yeah, so the angle of incidence equals the angle of reflection. So here, if I put it in kind of sideways here, you see that they come in, they hit, and then they bounce off like this. Do y'all see that? Yeah. And so it creates this interference pattern where they're overlapping here. And if you look like here on the corners here, you can see some diffraction where it's bending around the edge. Okay, so that's a nice flat barrier. But what would happen if I use this guy? What do y'all think? So if I put it down like this, what's going to happen?
It's going to curve.
So the wave comes in, and it hits and it bounces straight back. But if it hits the side here, it's still angle of incidence equals angle of reflection. So you'll see how it's making this kind of like curved wave when it's coming off of it. And again, there's really no waves behind it here. It's nice and calm back here. So what would happen if I turn this barrier around? What do you think? It almost looks like a drop of water. Y'all see that? That I have like these circle waves in the middle here. And then I have these plane waves coming in. So the plane waves are coming in, hitting the barrier, and they're coming to this focal point. Y'all see that? And so they create this circle wave pattern. Well, one of the interesting things about that, turn these off for a second, let that calm down, is that what goes in must come out. So here I have a little dropper, and I'm going to drop a little drop of water. And so if I drop it here on the side, you'll see it makes those curved waves that they bounce off it. So if I drop it right in the center, into the focus, I can make circle waves come out, but when they hit the barrier, they'll all come out together as a plane wave. There it goes. Do you all see that? The reflected wave is in a straight line. So it's just like math, that if you multiply something, you can get rid of that with division. So here, I can use circle waves to make plane waves, or I can use plane waves to make circular waves. So any questions about that? What?
Are plane waves just the ones that are straight like that?
Mm-hmm.
Okay.
Yeah. Anything else? All right, so we got one more for the wave generator here. Get it off the table. All right, so this is a fairly translucent piece of plastic here. So I have to cover it with water. Okay. So I've got this piece of plastic here, and I'm going to turn on this wave generator again, and it's going to make these plane waves that come out straight from the generator. But do y'all remember what causes the speed of the wave?
The source?
No, not the source. The medium. So what have I done here with the medium by putting this piece of plastic into it? What have I done to the medium? Is it all the same depth now? No. And so what happens here, turn this on a little bit, you can see the waves are coming out, and if you look along the side here, the side over there, the wave just keeps going. Do y'all see that?
Yeah.
But in here, do you see how this, you get this kind of a weird thing going on in here? Do y'all know what that is? That is the refraction of a wave. Because remember, with water, the depth affects the speed. So it's actually going slower here because it's shallower. Y'all see that? And so the wave has to slow down, which is why it's behind here inside of this piece of yellow plastic. So this is refraction. It's the bending of a wave because it's changing from one medium to another, or changing to speed. Did everybody see that? All right, so any questions about any of this? All right?
Why is it slower on the shallow?